the introduction, and thank you for having me back at Jay on the Beach. Jay on the Beach is a very special event to me because when I was here at 2016, this was one of the first talks I gave, and it went really well. The community was amazing, and it gave me the confidence as a PhD student that I was at the time to go out into the world and give talks to all different audiences and all different events. So it's really special for me to be back here, especially now, actually, because this is my first in-person event since the pandemic as well. So in many ways, it's my first conference all over again. As you can see from the title, today I'm going to be talking to you about the challenge of how we can build secure, trustworthy systems on top of the cloud. So how can we build systems that are confidential, integral, highly available, things that are really, really worthy of our trust as a community when we're running them on top of untrusted infrastructure? And as you can see also from the title, I'm going to be talking to you about the Confidential Consortium framework. This is an open source framework, as the name would suggest, that we built to help make it easier for application developers to build distributed systems with strong guarantees. Now, I could talk about CCF all day, but I'm sure I would be booted off the stage quite quickly. So today's talk is just a few highlights about CCF and a few of the things that I think are particularly interesting to me, particularly as a former kind of academic in the space of the theory of distributed systems. If you do want to learn more about CCF, I suggest heading over to the website ccf.dev, and from there you can find everything from academic papers to links to our source code. And if you're anything like me and you just want to dive straight into the GitHub repo, then you can head on over to github.com/Microsoft/CCF. So I think it's completely non-controversial to say that digital systems are absolutely integral to every single aspect of our lives, whether it's education, medical applications, transportation, government, finance. Digital systems are absolutely everywhere. We, as you might have seen, had some faff trying to get digital systems to work for us today. But they're incredibly important. They allow us to do so much. In some cases, our lives literally depend upon these systems, and they handle some of our most sensitive personal data. When you think about systems in education that store data about your children, or medical systems that store the most kind of intimate personal data about you. So it's incredibly important that we trust these systems. And these systems are just becoming more and more common. Like, I love technology, and I'm so excited for what the future has to hold. I'm so excited for everything from, self-driving cars to machine learning to many of the things that we're going to be hearing about over the next couple of days. So what could possibly go wrong with these systems? Well, unfortunately, the answer is rather a lot. So I am a Facebook user, and like quite a few Facebook users, I got this notification like 3 weeks ago that said there'd been a data breach and that I could join some kind of lawsuit thing. I googled it because I thought it might even be a scam. I just searched like Facebook data breach, and there were so many results I didn't actually know which of the one corresponded to the notification that I've had. So this was just one that I took a screenshot of, and this is an example of where one of these systems has had a data breach and confidential information about individuals has been revealed. This is bad for users such as myself, but this is also bad for companies. This was very expensive for Meta when it happened. So it's clear that confidentiality is an important problem in our computer systems. Secondly, I am British, if you couldn't tell from my accent. And in Britain, we have a postal service called the Royal Mail. It's famous for these big red letterboxes. And we have our local post office where you go and you send mail. And the post office is run by sub-postmasters. And so that's kind of your friendly neighborhood person who manages the post office. And these are generally quite beloved people in British society. And unfortunately, between the year 2000 and 2014, 900 of these people were prosecuted and found guilty of committing fraud and stealing money from the Royal Mail, the British Postal Service. And these people were made to pay back the money they had stolen. They were fined. They were imprisoned. Some of them were in prison for a long time and even died in prison. And so this is quite a sad thing that these people had done this, except that they hadn't actually done anything wrong. There was a software system, the Horizon system, and there was a bug in the software that was an accounting issue, and these people had been found guilty of stealing this money that they had never taken. This was in fact entirely a software bug, and this has been called one of the biggest miscarriages of justice in British history. So it's clear that integrity is a fundamental problem that we want in our computer systems. And thirdly, I was one of the people who was in a shop when I found out about this famous outage. So this was the Visa outage that happened in 2018, where the Visa payment network just went down. And like many people, I don't even carry cash. So I'm left there standing thinking, how am I even going to pay for these goods that I've already picked up off the shelves? I've taken a digital system and I've just become completely dependent upon it and dependent upon its availability. So availability is also a key property in systems. So it's clear that systems let us down. So should we trust them? Are these systems trustworthy? What does trustworthy even mean? I'm a distributed systems person, so I love answering any question with a 3 or 4 letter acronym. If it's the CAP theorem, FLP, acid, base, I want a 3 or 4 letter acronym to define a set of properties and then try to reason about whether we can have them all or not. So, with that spirit in mind, here's a triangle and a 3-letter acronym. So, the first letter we have is C, and C is for confidentiality, so protecting data from unauthorized access. We saw this in the first example with Facebook. Secondly, we have integrity, protecting data from unauthorized modification. This is something or accidentally incorrect modification. This is something we saw with the post office example. And thirdly, we have availability. We depend on these systems, so we need them to be online and available to us when we want them, even if there's been some failures in some of the underlying components. And this is what we saw with the Visa outage example. And together, these form the CIA properties. Now, CIA properties aren't the only properties that we need for a system to be trustworthy, but it's clear that these are very desirable properties. Unfortunately, however, these properties are in conflict with one another. When we think about a system, for instance, that's confidential, we think about data that's private, data that's encrypted, data that's very much secret. But when we think about a system that's acting with integrity, we might think about systems that are quite transparent, systems that are quite public, systems where we can see what's going on inside. And so there's a clear contradiction here between confidentiality and integrity. And then we have availability. One of the main ways we get availability is through replication. So we have some state and we replicate it in some different places, across some different availability zones, different systems, different cloud providers even. But this is in direct conflict with confidentiality, because where you previously had one system to secure, you've now just made yourself N systems to secure. And then we've got integrity problems, because now we need to keep these systems in sync somehow and make sure that we have consistency across them. So the CIA properties are incredibly difficult to achieve. And it's not just the fact that these properties are in conflict. Actually, I think that the way that we're building systems means that they're only going to get harder and harder to achieve as time goes by. One of the main reasons for this is cloud computing. Now, many people absolutely love cloud computing. It gives us so much, right? It's really easy to use. You can get started very, very quickly, but then have access to global infrastructure. You're finally freed from the burden of having to manage machines, and you can pay someone else to deal with this for you. There's lots of great reasons to use cloud computing, and as we've seen, many people do. But fundamentally, what cloud computing means is running your software on someone else's infrastructure, and that's going to make it much harder to achieve the CIA properties. And thirdly, we have the fact that as we're building more systems and we're becoming more dependent upon them, we're going to need different organizations to work together to build these systems, and they're going to want to collaborate, they're going to want to share data, they might want to do things like machine learning across shared data sets. So the question naturally arises, how can we do this in a way that it protects confidentiality, integrity, and availability when the parties who are involved in creating this system don't even trust each other? So there's a bit of a trend at the moment that these talks always have to have a banking example because of blockchains and stuff. So here's a piggy banking example. Imagine we have 3 banks. We've got the green bank, the yellow bank, and the pink bank. And we've got 3 bank customers, Alice, Bob, and Charlie. We can see Alice. Alice is quite rich. Alice has got $3. We can see Bob. He's actually got $4 if you look across the 3 banks. And Charlie, bless him, he's only got $2. So you can imagine a situation where a financial regulator or a tax authority might pop up and say, we need to know who the high net worth individuals are. So banks, can you tell us between you which customers have at greater than or equal to $3 across the 3 different institutions? So here you can see the result of this query should be Alice and Bob. And there's 2 ways that we could implement this. Firstly, the regulator could talk to each bank and say, tell me which customers have at least $3. And the green bank will say, Alice does. And then the yellow bank and the pink bank will say, none of our customers do. This is great from the perspective of privacy because the data on the customers like Bob and Charlie isn't leaving these banks. But this is terrible from the perspective of the regulator here, who's going to miss out on Bob because Bob has quite cleverly split his funds across these 3 banks. The other way that you could do this is say, well, all the banks, they send all the information on all the customers to the regulator computes this sum, and then they can do all the queries they like. And this is great from the perspective of the regulator. I'm sure they would love this. But that doesn't mean this is good from the perspective of privacy of customer data. So, can we do better? It's worthwhile acknowledging that whilst I am hopeful about the future of distributed systems, I do just want to acknowledge that no pragmatic system will ever be perfectly trustworthy. We will never be able to prove that a system is entirely confidential, completely integrity protected, and available 100% of the time, no matter what happens. Even if all the machines are off, the system would still be there. We can't have everything, but surely we can do better than the mess that we see in reality today. And this is where the work that I've been doing on the Confidential Consortium framework comes in. CCF aims to provide a pragmatic foundation for building multi-party applications on untrusted infrastructure and making it more trustworthy. That's a big sentence. Trying to fit CCF into one sentence is quite the challenge. So we can break it down a bit. Pragmatic. When I say pragmatic, I mean we want a general purpose solution. We want to enable application developers to focus on implementing their own applications, and we want to solve problems like confidentiality, integrity, and high availability for them so they can focus on the more important things. We want the system to support many different applications, so we're going to need it to be stateful. We're going to need to be very flexible in our approach. We're going to need to support different consistency guarantees. We're going to need to be pragmatic in the fact that we deal with catastrophes that might happen. We're going to have to deal with updating the system. We're going to have to deal with all that kind of stuff that happens in practice, but that I, as a recovering academic, used to be able to completely ignore when I was writing my papers. We also talked about multiparty. So this is the idea that you might want these banks, for instance, to be able to work together on a system without necessarily trusting one another. And we're going to be running on untrusted cloud infrastructure. And we want it to be more trustworthy, which goes back to the CIA properties that we talked about before. And this is what we're trying to do in CCF. So CCF is kind of 3 things in one. Firstly, it's a foundation for doing research into distributed systems, security, and privacy. So basically, it's a way that we do researchers, we come up with stuff, we put it into CCF, and we use that as a vehicle for making it available to application developers. CCF is also, it's an open source project in its own right, under the Apache 2 license. And if anybody is interested, it is also available in the form of 2 Azure services. So there's the Azure Confidential Ledger and the Azure Managed Confidential Consortium framework, which are both cloud services based on CCF. So CCF tries to achieve grand goals, and the natural question is, well, how does CCF manage to achieve all of these different things? Firstly, CCF uses trusted execution environments, which are a new hardware technology that helps us a lot with providing these CIA guarantees in practice. Secondly, CCF is built on an immutable distributed ledger with some interesting properties around its rollback protection and integrity protection. And thirdly, CCF has a really novel and interesting approach to doing transparent multi-party governance. Now, there's a lot more in CCF, but these are just my kind of 3 favorite things from the lens of distributed systems. So firstly, we'll talk a little bit about TEs. So when we think about systems today, we see that they have encryption at every step. So when you think about when you send packets over the network, nowadays, HTTPS has become the standard. There was a time when people said, no one's going to adopt that. We won't get the servers to change. We won't get the browsers to adopt it. And seems like those people were wrong. Like, HTTPS has become the standard now. And the same can be said for encryption for data at rest. This computer, because this is my computer that wasn't working. This computer, when it's working and when it's not, the hard drive is encrypted, and that's there by default and something we just take for granted nowadays. But there is a missing piece to this picture. We've got data in transit that's encrypted, data at rest that's encrypted, but what about data during execution? And this is something that we don't talk about that much as a community because we don't think that we have the solution for it. Fortunately, we do have a new hardware technology. It's been around for maybe like 6 years at this point, but it's still very much in its infancy, but it's becoming more and more popular, and that is trusted execution environments, or TEs for short. TEs provide a kind of secure chunk in the processor that has execution that is isolated from anything else that's going on. The memory itself is encrypted, and it has what we call remote attestation. The last one here is really cool. So basically it means that you can run your application inside the special TE, and you can send it a message over the network and say, prove to me that you're actually inside the TE, to prove to me that you are the software that I think you are. And you can basically produce a cryptographic proof that you can then verify to prove both that it is inside the TE and that the software is running as is and has not been modified in any way. There's various offerings from most of the major hardware providers. Probably the most famous offering is Intel's SGX, and Intel's new solution is called TDX. And AMD have various flavors as well, and ARM have their Trust Zone and Realms, which is the new version that's coming out soon. So you can get TEs in various places, and machines with TEs are available with various cloud providers. So these TEs are really, really cool, and they help us a lot with ensuring confidentiality and integrity of systems. That's wonderful, right? Doesn't that solve all of our problems? And unfortunately, the answer is no, it doesn't. So firstly, if we've gone some way to getting the C and the I, we now need to think about the A in CIA. And so as a distributed systems person, and as I mentioned earlier, how do we get high availability in our systems? Well, we replicate our state. So here you can see in this diagram that a developer writes some application logic, and CCF provides some code, and we seal it inside this T, the trusted execution environment, and then we replicate it, and that should give us some availability. So let's zoom in a little bit more and see how this actually works. So we've got these replicas. We're going to need to keep them in sync. If you saw my talk at Jay on the Beach in 2016, I was talking then about consensus algorithms, and these are a mechanism by which we can keep these replicas in sync. We elect one of them to be the leader, and they're responsible for deciding the order in which operations occur. So you can see in this diagram, we have users who send requests to the request handler that's provided by CCF. CCF checks that the user has permissions to send something to the application logic, and then the application logic will execute the request, and there's a key value store that CCF provides for storing state. Once the request has been executed, it's sent back to the request handler, and the request handler sends the response to the users. It sends the transaction that resulted from executing this request to the ledger, and it sends the request to some kind of consensus algorithm like a raft or a multipaxos, whatever your favorite thing is. And this diagram is quite typical. This is fairly bog standard state machine replication with a consensus algorithm. This is a nice, neat story. I've told this story for a long time. Unfortunately, this story quickly starts to fall apart in reality. And the problem, actually before I move over, the problem here is this thing at the bottom, the ledger. So this is just a record of what's happened in the system and transactions that have happened. And as you can see, the TE is up here and the ledger is not inside the TE because the ledger is a set of files that are stored on disk. And it's this persistent storage which is at the heart of why this is a tricky problem to solve. When it comes to the ledger, we have three really tricky problems. We have confidentiality again, so we now need to work out how do we protect that data when it leaves the trusted execution environment. We have integrity, so we want to make sure that the host isn't able to just modify the data. And we have freshness, or protection against rollback attacks. So how do we make sure that the host isn't able to return old state? And these three problems, which usually, back in my former life as an academic, I was able to ignore, are actually incredibly important in practice. And these are the three problems that we think we've solved in CCF. The first problem, confidentiality, that's not too hard to solve, right? You encrypt the state before you send it to disk, and now you're happy. The main problem comes when it comes to integrity and to freshness. So how do we achieve integrity protection? Let's imagine this ledger has a set of transactions in it. We've got 4 user transactions here, and we want to somehow ensure the integrity of this set of transactions. The way that we do this in CCF is we introduce a special new transaction called the signature transaction. And the signature transaction, basically as it sounds, includes a signature over the ledger so far. We want a fairly efficient way of producing these signatures that doesn't require us to redo too much work each time we need to generate one. And so we use a binary tree of hashes, also known as a Merkle tree, to generate this signature. So here you can see the tree, and then the root of the tree is included in the signature transaction. And this is what gives us integrity protection of this ledger. So this is what ensures that our system as a whole has integrity. So the third problem and final problem was this freshness problem, or protection against rollback attacks. So the host, if they wanted to, could truncate the ledger, or they could roll it back to the last signature transaction. So you could have a ledger that looked like this, and the host could pretend it actually looks like this. And most of the alternative systems in this space, and most of the academic papers in this space, they try to come up with these heavyweight mechanisms to prevent hosts from doing this. And so they really actively try to fight it and stop this from ever happening. Interestingly, with CCF, we took quite a different approach, which is to say, let's just live with it. Let's just accept the fact that the state that's on disk might not be up to date. And in fact, this isn't that novel. This is quite a standard assumption in distributed systems, because if you want to ensure that state is up to date, you have to, every time you write it, you then have to wait for the write to happen. You have to call fsync. This can be very slow. And so we're basically kind of returning to this idea of saying, actually, we'll just accept that the state on the disk might be behind. And the CCF therefore has a kind of quite novel and interesting reconfiguration algorithm that allows it to atomically switch from one set of nodes to another. And this is really important because with the live with it approach, when one of these nodes, be it follower or leader, dies in a CCF network, we basically cut it off and we're like, you're dead to us now. We don't want to know you. If you want to come back and participate in our system, you're going to have to go through a reconfiguration procedure and essentially join like you were a new node. So there's no allowing you to restart and just pop back up and carry on, like everything is good. So the third thing I mentioned was this transparent multi-party governance. And to me, this is easily the most interesting part of CCF. Remember, we had these little banks who might want to work together to run a system. Well, eventually, anyone who's worked with systems will know that at some point you're going to have to update the system, and you're going to have to change the permissions or change the set of users, change who's allowed to execute requests, or you want to change the set of nodes, so you want to move the system from one place to another. These are all general maintenance operations that are an inevitable part of everyday life when it comes to running a system. Unfortunately, we work so hard to have these guarantees and to say that we want to have confidentiality, we want to have integrity, we want to have high availability. So how can we do these things without sacrificing our CIA properties? And this is tricky, right? Like, my bank must contact me like once a month being like, our system's going to be down for 6 hours because we're upgrading it. And I'm like, why can't you work out how to upgrade your system without taking it down? And so we want to do that whilst also preserving the confidentiality and the integrity properties. And again, in my former life as a researcher, it was very much, this was the kind of thing that I could very much ignore and put my head in the sand and say, it's fine, it's good. No one ever needs to update their systems. No one ever needs to migrate their systems from one place to another. But the reality is that these things are incredibly important, and they're often the weakest link in the chain when it comes to a guarantee like confidentiality. So the way that we do this in CCF is we say that CCF is going to be governed, any CCF service is governed by a consortium of members. So the consortium could be, for instance, these 3 banks, our green bank, our yellow bank, and our pink bank. And any change to the service that we're going to have is going to have to require this consortium to agree to it before it goes ahead. So we need to make sure that all 3 of these parties are on board before we can make a change to the system. Otherwise, we could easily violate the confidentiality and integrity guarantees that we have for the system. And we need to do this whilst maintaining availability. So the system has to stay up, and we have to be able to do things like update the logic of the system. And this is where CCF has this quite interesting notion, which I call like ballots and proposals. So every change to the service starts as a proposal sent by one of the consortium members. The consortium member sends it to the leader, and the leader creates what's called a governance transaction. So if you remember that ledger at the back end that we were using to store transactions in our system and keep state up to date, well, CCF is using that system for itself and for its own maintenance as well as using that for user transactions. So once the leader creates his governance transaction, it replicates it to its followers. And then other consortium members, in their own time, we're not stopping the world, we're not, everyone can do things when they want to do it. The other consortium members come along and they submit ballots saying, I'm in favor of this change. I vote that it is good to upgrade the application logic, or, yeah, I agree with migrating from this set of nodes to this other set of nodes. And the leader, again, creates governance transactions for these ballots and replicates them to the other nodes. Eventually, when the last of the majority of the consortium members agrees to a change, then the change can go ahead and be executed. What's really neat about this is that we now have a full record on that ledger of all the nodes of exactly who proposed that we were going to make this change and all the parties that were involved in signing off on this change happening. This is really useful from the perspective of transparency and auditability for us to be able to look back in history and work out what happened and why. So if we go back to our example with the 3 banks, we can imagine the green bank saying to the yellow bank, well, should we update the app so that we can see all of Pink's customer data? And the yellow bank says, sure, why not? You can audit this after the fact, but, until then, I get a whole bunch of secret data. And the pink bank is like, wait, why wasn't I part of this decision? But if we're just saying you need a majority of votes, then just the green bank and the yellow bank will be enough to change the application in any way and violate the confidentiality and integrity guarantees. So it's clear from this that there isn't a one-size-fits-all when it comes to governance. So just saying the majority of the consortium members have to sign off on something clearly isn't enough in practice. And so the way the CCF deals with this is it has this notion of a constitution. So constitution is literally a set of JavaScript that describes what actions can be taken, what maintenance and governance actions can be taken, and what the voting criteria is for every action. So you don't have to give the members the same voting power, and you can change the rules for different operations. So for instance, if you want to update the application logic in this example with the 3 banks, you would say, actually, according to the constitution, all 3 of the banks would need to sign off on an update to the application logic, because it could violate the confidentiality of any of the data of their customers. So with CCF, we are trying, and it's very much an ongoing project, to enable application developers to build confidential, integrity-protected, and highly available applications. And this is by no means without its challenges. The first of which is that these trusted execution environments, whilst they're really, really nice in theory, in practice they've been subject to quite a few attacks. In particular, Intel SGX, which is the most widely used of these TEs. Many students have got PhDs basically out of attacking Intel SGX. And I think at the moment we're in this in-between stage where there's a few attacks for the newer hardware, but we're not really sure whether we're going to see the SGX effect again, where these attacks become very, very common, or if this was just a teething problem with a new bit of technology. And this is very much something we're trying to watch and keep an eye on in CCF. Secondly, CCF does still trust the hardware manufacturer. So CCF is all about allowing you to build applications that are trustworthy even when you're running them on the cloud. So you're not trusting the operator of those CCF nodes, but you are still trusting the hardware manufacturer, be it Intel or AMD or ARM. Thirdly, TEs might guarantee that the code itself is executed correctly, that it has integrity, but they don't guarantee that the code is correct. And this is, I think this is a big problem, and something that we could really do with addressing is that we don't really know whether the code itself is correct. And in the case of CCF, for instance, it's an open source project. You can very much go and read it. It's written in C++. It's quite big. So good luck to you. I think it would be really cool, and some of the research that I'm doing at the moment is about formal verification and automated proofs, and how we can actually design code that is correct by construction, and so that we can trust both that the code is executed correctly and the code itself is correct. And fourthly, the consortium members are together collectively trusted. So in the case of the 3 banks, we said that those 3 banks would all need to sign off on any change to the system. Well, they could get together and sign off on any kind of change that could happen, and that could, for instance, be revealing all the data of all the users. Now, obviously, it's not a good thing for them to do that, and they wouldn't want to do it, but you are collectively trusting the members of the consortium. So that is something to bear in mind, particularly as a kind of when you're writing constitutions, you're thinking about how do we want to make changes to the system, who needs to be involved in signing off on these changes. So in summary, I do really think it's worth rethinking the trustworthiness of our systems, particularly as we migrate to the cloud and we are increasingly integrating our systems and looking to share data and share applications across different organizations. We identified 3 properties that are really useful when it comes to reasoning about trustworthiness. This is confidentiality, integrity, and high availability. Sorry, that was meant to be on there. CCF is a pragmatic framework to help application developers make their apps more trustworthy without having to worry about the intricacies of confidentiality, integrity, and availability. But even if CCF isn't the right approach for an application, I hope that we as a community can take some things away from the design and from things like the use of TEs and using voting protocols to decide when we're going to migrate the system from one set of nodes to another. CCF works by combining trusted execution environments with a distributed immutable ledger and multi-party governance to improve the confidentiality, integrity, and high availability of our systems today. That's it from me. I am super excited to hear what questions you have. And if you want to learn more about CCF, then please take a look at the ccf.dev website or catch me around in the hallways, probably drinking some coffee. Thank you so much.